What if I told you that math isn't really about crunching numbers? Seriously, what if it's actually a language, a powerful descriptive tool that we use to make sense of, well, everything, from our own thoughts to the very fabric of the universe?
So let's just try a thought experiment. What if mathematics was actually a secret map of reality? And like any good map, it has a key, a legend, to help us navigate all that complexity.
So today, that's exactly what we're going to do. We're going to explore this A to Z framework that treats math like a meta-mathematical cartography. Fancy term, right? It just means a map of meaning. We're not going to hit every single letter, but we'll stop at some key landmarks that reveal a whole new way of seeing things.
So here's our game plan, our journey across the map. First, we'll tackle the grammar of relationships. Then we'll use that to map the physical world. From there, we'll dive into the architecture of systems. And finally, we'll put the whole big picture together. Ready? Let's jump in. Okay, first step, the grammar of thought. This is ground zero. It's where we learn the basic language of our map, the abstract symbols that let us chart a course through really any idea. And where else would we start but with A for algebra? This is our starting point because it gives us this incredible power to talk about relationships in a really general way. It's the language that lets us get beyond specific numbers and describe the patterns that govern them. And that's huge because this is the actual syntax of thought. Algebra teaches us something so profound that truth isn't always in the numbers. It's in the relationships between them. All right, next stop, B for Boolean logic. This is that simple but super powerful logic of binary choices, true or false, on or off, 1 or 0. It's the most fundamental decision-making tool on our map, that point where any path either exists or it doesn't. And don't let that simplicity fool you, because it is profound. Boolean logic is the logic of distinction itself. I mean, it's the bedrock of all digital computing, proving that even the most complex systems can be broken down into a series of simple yes or no questions. Okay, so we've got our basic grammar down. Now let's get a little more adventurous and head into a new region of our map, the one we can actually see and touch. It's time to map the physical world. So let's jump ahead on our map to G for geometry. This is math's toolkit for describing the actual physical shape of our world, the forms, the spaces, the dimensions that we navigate every single day. This is really where math becomes tangible, embodied. Geometry is that amazing intersection where pure abstract logic meets our physical intuition. It's how we recognize structure in the world around us and just instinctively know symmetry when we see it. Okay, let's fast forward a bit on our map to K for kinematics. Now, this isn't about why things move. That's getting into physics. Kinematics is the pure mathematical description of the movement itself, a trajectory, a velocity, and acceleration. And when you look at it this way, it really does turn motion into a story. Kinematics basically treats time as just another dimension of geometry, framing change as a path you can trace on a map. It's the narrative of where something has been and where it's going. All right, for our third leg of the journey, we're zooming out. We're going from mapping single objects to understanding entire systems. We're on the hunt for the hidden order and how complex things fit together. So how does math even begin to model these systems? Well, we start with two basic types. You've got L for linear systems. Those are predictable, they're proportional. Double the input, you get double the output. And then you have Q for quadratic systems. They're the first, simplest step into the nonlinear world, capturing all the curves and turning points we see in real life. But what happens when you have a system with tons of variables all at once? Well, that brings us to M for matrix. The best way to think of a matrix is like an elegant, super organized filing cabinet for information. It's this structured grid that can hold all the different relationships in a really complex system, letting us represent transformations and connections all in one neat package. The thing to really get here is that a matrix isn't just some boring box of numbers. No way. It's the architecture of relations. It lets us see systems within systems, and to understand that even a really complex transformation has a hidden structure all its own. And here we are entering the final region of our map. We've laid the foundations, we've charted the physical world, and we've structured complex systems. Now it's time to put all the pieces together and see the big picture. And that synthesis begins with S
for summation, which you'll often see as the Greek letter sigma. And it's really just the simple act of adding things up, of taking all these individual pieces from our map and creating one complete view.
But on our map of meaning, this is an incredibly powerful act. Summation is the mathematics of wholeness. It's how we create a complete picture by carefully counting and combining all its parts. It's synthesis through enumeration. And finally, we arrive at x, y, and z. This is how we build our dimensional reality. The x-axis isn't just a line, right? It's our baseline, the input, or maybe the progression of time. The y-axis is the result, the consequence that emerges from that baseline. And the z-axis? Well, that's the cool part. That's the unseen layer of depth, the hidden complexity that gives our map a rich third dimension. And just like that, we're at the end of our journey. We've used this A to Z framework not to calculate, but to navigate, to travel from these abstract symbols all the way to a rich, dimensional understanding of reality itself. So let's just quickly retrace our steps. We started with the basic grammar of relationships, right? Then we used that to map physical space and motion. After that, we uncovered the architecture of complex systems. And finally, we assembled it all into this multidimensional view of reality, revealing math for what it is, a powerful descriptive language. So the big takeaway here is that mathematics isn't just some complicated tool for specialists. It's a universal map of meaning that's available to every single one of us. It provides the framework, the paths, the coordinates. The only question left is, what will you discover with it?